A picking interface seamlessly connecting passive and active performance on guitar. Introduction. We have designed an interface that allows a guitar player to manipulate another channel, such as the manipulation of sound and visual effects, while playing the guitar. The feature of our interface is that it connects passive and active performance seamlessly. Passive performance refers to a state in which the performer normally plays the guitar, and the interface automatically applies sound and visual effects. For example, when playing the guitar, the picking motion itself is sensed and the parameters of the sound effects are automatically adjusted. On the other hand, active performance refers to a state in which the player actively manipulates the effects through the interface when the player is not playing the guitar. For example, when the performer is not playing the guitar, visual effects can be switched by some action, like pressing the pick or by shaking his or her wrist. Our goal is to create an interface that immediately reflects the performer's intentions visually and musically without turning away from the guitar playing motion. Related works. There have been many studies in pattern recognition on the guitar. For instance, one study proposed a method that detects and classifies guitar techniques by analyzing note, pitch, and attack of guitar sound. Another study investigated a recognition technique of guitar playing based on F0 sequence. These studies recognize guitar techniques by analyzing data from guitar playing. However, these sensing techniques cannot be used directly for the purpose of this study, namely, picking state identification. Proposed method. In this paper, we propose a method to recognize guitar picking state by using pressure and acceleration sensors. In addition, we present an audiovisual application. This application enables performers to extend their expression by converting their picking hand motion into visual and sound effects. Picking states. For our goal, seamlessly connecting passive and active performance on guitar, recognizing whether picking occurs or not is needed firstly to clarify whether ongoing performance is passive or active. We think it is also useful to recognize picking styles, such as chord stroke and single note, to give effects variation to active performance. Therefore, we judge the current state as non-picking, chord stroke, or single note. Our interface. Our interface consists of a pressure sensor and a 3-axis acceleration sensor. The pressure sensor is fixed onto a guitar pick. It senses pressure force between the thumb and index fingers of the player's picking hand. The acceleration sensor is fixed on the first knuckle joint of the index finger. It measures how much the picking hand has rotated. Classification. Table 2 shows the classification of pressure patterns. We separated pressure force into 3 categories: strong, weak, or jitter. Firstly, we judge the state as strong if the pressure value is higher than one threshold. Secondly, the state is set to jitter if the pressure rapidly changes. Finally, a state that does not satisfy the both of strong and jitter is determined as weak, which means a non-picking state in which the player is just pinching the pick. This is a movie of strong recognition. When the pressure value is higher than one threshold, strong flag turns on. This is a movie of jitter recognition. Specifically, it indicates a state that the difference between the original pressure value and the pressure value after applying the low-pass filter exceeds a certain threshold. Table 3 shows the rotation angle pattern classification. We determined the rotation states to be narrow, wide, or stationary. Firstly, we judge the state as wide if the rotation angle fluctuates greatly. Secondly, the state is set to narrow if the rotation angle vibrates quickly or a small amount. Finally, a state that does not satisfy the conditions of wide and narrow is determined as stationary. This means a non-picking state, in which the player is not moving their wrist in a picking motion. This is a movie of wide recognition. Concretely, we calculate the root mean square of the difference between the original rotation value and the rotation value after applying the low-pass filter, and then judge the state as wide if the RMS exceeds a certain threshold. RMS was adopted to measure the continuous intensity of wrist rotation during the chord stroke. This is a movie of narrow recognition. Specifically, it indicates a state that the difference between the original rotation value and the rotation value after applying the low-pass filter exceeds a certain threshold. All of the threshold values are selected through trial and error, depending on the individual picking style. By combining these two factors, pressure and rotation angle, we judge the picking state as non-picking, single note, or chord stroke. Firstly, if the picking state is jitter and wide, we determine it as chord stroke. Secondly, if the picking state is jitter and narrow, we determine it as single note. Otherwise, we define the picking state as non-picking. Experimental result. We informally tested our prototype interface. One of the authors has been playing the guitar for 5 years. He sequentially played the guitar with our interface in the order of rest, single note picking, short interval, chord stroke, and rest for about 12 seconds. In this graph, each column shows the value of the pressure sensor and acceleration sensor respectively. The horizontal axis indicates the number of frames at 60 frames per second. This graph shows the result. Each column shows non-picking flag, single note flag, and chord stroke flag respectively. The value takes 1 or 0 on each flag. As a result, basically the 3 picking states are classified correctly. This graph shows the comparison between sensing data and the flag. Comparing the start point of single note picking in raw data pressure and the rising edge of the single note flag around the 50th frame shows that the latency for single note state recognition is very low. In the vicinity of the 320th frame, the non-picking flag rises for a moment and then falls immediately. This is because there was an interval when moving from single note playing to chord playing in actual performance. This also shows that the latency for single note state recognition is small. On the other hand, latency of about 30 to 40 frames occurred in the recognition of the chord playing as shown from the rising edge at 360th frame and the falling edge at 590th frame of the chord stroke flag. This is presumed to be due to the use of the RMS calculation for chord stroke recognition. Application example. We present an audiovisual application example. This application enables performers to augment their visual and sound expression through their picking hand motion. Visual expression. In the non-picking state, as an active performance, the performer can manipulate CG effects by associating the pressure with the expansion rate and the rotation angle with the colorfulness of the sphere. Also in the picking state, as a passive performance, the interface automatically applies CG effects. For example, during the chord stroke, the RMS value affects the rotation speed of the sphere, therefore the intensity of performance and rotation of the sphere are synchronized. Sound expression. The performer can also manipulate sound effect parameters by picking. In the non-picking state, as an active performance, the performer can manipulate sound effects by associating the pressure with the dynamics effect, and small wrist shaking with the delay effect. Also in the picking state, as a passive performance, the interface automatically applies sound effects. For example, during the chord stroke, the RMS value affects the degree of distortion, therefore the intensity of performance and the intensity of the guitar sound are synchronized. Conclusion. In this research, we proposed a method to discriminate ways of picking by sensing pressure and rotation angle in a player's stroke movement. As a result of the experiment, 3 picking states can be correctly distinguished through our interface. We also introduced an application example which manipulates visual and sound effects through our interface. We will improve the latency in the future.